Welcome to Chem Vid. Today we are talking about the mole. No, not the cute fuzzy little creature, but the mole, the counting number. So first, let's get started with defining some terms. Atomic mass. That one's pretty simple. It's the mass of an atom. Alright, and they're measured in AMUs, atomic mass units. They're on the periodic table. They're the very bottom number. Formula mass, however, is the mass of a formula, or the mass of a compound. So mass of a formula is also measured in AMU. If I look at atomic mass is like the mass of one hydrogen or one oxygen. And when I look at the periodic table, it's listed right here at the bottom. A formula mass is when I have a formula such as H2O or NaCl or any of those compounds where I have two or more elements bound together. And then it's the total mass of them put together. So since oxygen is 16 and water is 2, and I have 2 of them, I'm going to add those two together and I get 18. So, formula versus atomic, both the same thing except for we're talking about element versus compound. Now, molar mass is the one that we're going to get into today, hence the mole part of our notes. So if I look at molar mass, this is the same thing as the atomic mass units, except for the units are grams, how many grams there are per mole. Alright, so the units for molar mass are grams per mole. We're going to find out that the mole is a counting number, and then grams is how many grams you would measure out, like in your laboratory. Okay? But the molar mass is just the mass of an atom, or it's the mass of a formula, but the units change. So the units are really important for molar mass. Alright, so where do you find the mass of an element? You find it on the periodic table. This lovely little mass right there is the mass of the element. It is measured in AMUs, but as we learned before, it's also measured in grams per mole. So this is also the molar mass. Okay? So let's take a look. What is the mass of carbon? I look over at carbon, it's 12. Hydrogen is 1. Oxygen is 16. What happens if we have a compound? I just add all of it together. Oxygen is 16. I have 2 hydrogens, which are 1 each. So 18 total. If I take a look at the mass of these lovely characters, go ahead and try to add up all the masses for the male hormone and the female hormone and see if you can get it correct. So testosterone weighs 208 grams per mole, meaning for one counting unit, it weighs 208 grams. On the other side, estradiol weighs 272 grams per mole. So, what are these units? These units are how we connect theoretical chemistry of all those tiny little molecules into real life laboratory. We are actually able to use them, okay? So grams per mole allows us to connect the theoretical with the actual and allows us to do chemistry in real life. Very important. So to introduce you to the mole, I would like you to go to YouTube and I'd like you to watch this YouTube video right here. You can also go to YouTube and type in how big is the mole, and it's the TED Ed video. It's 4 minutes and 32 seconds. Please watch this video before you continue the notes. Alright, hopefully now that you've watched that video you have a bit of an idea of what the mole is. We're just going to review it real quick. So the mole is a cute little creature that lives underground that has really long fingernails. But that is not the mole we're looking at. The mole we're looking at is the one discovered, or the idea discovered, by Avogadro. If you look, he was a count and an Italian scientist, because back then the only scientists that were financially able to study science were the nobility of the Italian and European and French courts. So he discovered that if you take two different gases and put them in the same pressure and the same temperature, they had the same number of particles in there. Even though they had different masses and they were different substances, the number of substances was the same. And this was really different. This was such a new idea. So he went and he was like, yeah, I'm going to tell everybody about this. And guess what? Nobody believed him. They all were like, what? You can't even prove this. And it was right. He couldn't. So, late 1860, guess what? They found out that, hey, there are little particles. We do have compounds. We do have elements. There is a difference between those two. And everybody was so excited. But you know that Avogadro died earlier, so he never even got to see the fruits of his labor. But his contribution led to the naming of the mole, Avogadro's number. The mole is just a number of particles. So since elements and molecules are so small, we use 6.02 times 10 to the 23rd of all those tiny little things in order to blow it up into our laboratory use. So we actually have enough water and enough molecules to react and to do things in real life. So, how big is that number? Well, you took a look. A mole of donuts would cover the earth many, many times and be 5 miles deep. Basketballs, if we had a mole of basketballs, we could create a new earth. If you received 1 mole of penny on the day you were born and spent $1 million every second until you died at 100, you would still have 99.9% of the money left over. A mole is a gigantic number, one that is very hard for really any of us to understand. Scientists have been using it for so much that it becomes more understandable to them, but this is a really, really big number, okay? So chemists use moles to count molecules, like you would use pounds to count grapes or salami. When you go to the store, you don't buy 5 grapes or 10 grapes or 100 grapes. You buy a pound of grapes or a pound and a half of grapes. Counting each individual grape would be tedious for the person ringing you up, right? So we use pounds. Well, it's the same thing with moles and molecules. Trying to count up enough water or enough hydrogen or enough oxygen in order to create a reaction it would take you forever. In fact, you would die before you would ever be able to count that many elements. So instead, we measure it by the counting unit mole. So if I want 1 mole of water molecules, then I would actually get 6.02 times 10 to the 23rd water molecules, and it's much easier to just say 1 mole. So, how many are in the jar? Well, if I look at that jar, it looks like it's about half dozen. How many M&Ms are in this jar? Well, it looks maybe there's like 200-ish, okay? How many? Oh my gosh, I can't even count the number of sand particles that are in that jar. I would probably use 1 billion or maybe use a prefix in order to help me out there. So, we have this video, and if you haven't watched the video already, make sure you do. But counting numbers are used all around us in everyday life. So go ahead and take back out your notes, and we're going to go over the different counting numbers. Alright, so first, 1 pear is equal to 2 shoes, or 2 carrots, or 2 computers. If you notice, 1 pair, it has nothing to do with what you're counting with. A pair is always 2. A dozen is always 12. A ream is always, anybody know? 500. A ream, usually we use it for paper. A ream is 500 sheets of paper. A ream can also be used to describe how many TIE fighters you have, or how many bunnies you have. Interesting fact, a large group of bunnies is known as a fluffle. Thought I'd let you know that. Alright, so all of these guys are counting numbers. The mole is just the same thing as one of those. 1 mole is equal to 6.02 times 10 to the 23rd of anything. So you can do molecules, you can do particles, you can do hats, you can do droids, you can do anything you want. 1 mole just means 6.02 times 10 to the 23rd. It's just a counting number. Okay? So, the mole, we have this wonderful number. It's so big it's really hard to understand, but it makes sense since we're using tiny little particles like atoms or elements. So, since the mole is so hard to comprehend, we use dimensional analysis to help make the conversions easier. So if you're wondering when we were going to get started with dimensional analysis, now is the time. We are going to use dimensional analysis to start talking about this big, big, big number. Alright? So, practice. Go ahead and try 8 and 9. If you have 36 donuts, how many dozen donuts are there? How many reams of paper will you have if you have 2,125 pieces of paper? But here's the catch. You need to do it using dimensional analysis. So pause the video, take a moment, and try to figure this out using dimensional analysis. Okay, so 36 donuts. The unit of donuts goes to the bottom, and I want to get to dozen, so that goes on top. 12 donuts equals 1 dozen. Remember, this guy, this conversion factor, never changes. It's always what equals what. Okay? So I put the number I start with, or the number I want to change out front, and then I use conversion factors. After I've done that, I multiply by what's on top, divide by what's on bottom, and I get 3 dozen donuts. For pieces of paper, I start off with 2,125 because that's the number I want to change. And there are 500 pieces of paper in one ream. My units cancel out, and I am able to get 4.25 reams. So the important parts of dimensional analysis are: always make sure to start with the number that you are trying to change, the number you want to change into a different unit. Make sure that your units cancel out, so you're left with the unit that you want. Pieces cancels out with pieces, and I'm left with reams. Units are really going to help you, especially when you're still learning this weird world of moles. Okay? Then, the next part is make sure you always multiply by top, always divide by bottom. Use sig figs, of course, and then use your units. So with sig figs, I have 2 sig figs here, so I would need 2 sig figs for the answer, so 3.0. I have 4 sig figs over here, so I would need 4 sig figs over here, so 4.250 reams. Done and dusted. So let's try this with our new friend, the mole. Okay, so number 10. How many zinc atoms are there in 2.5 moles of zinc? 2.5 moles of zinc? That's what I want to change. I want to know how many atoms are in 2.5 moles. So 2.5 moles of zinc. That's what I start off with. Alright, 2.5 moles of zinc. Then the moles, that's the unit I'm trying to change. So I'm going to put that guy on bottom, moles of zinc. And then I want to get to atoms. It tells me that I want to get to atoms, so I'm going to put atoms up here. Atoms of zinc. Now, this is where I start using my numbers. I know that Avogadro's number, or 1 mole, is always equal to 6.022 times 10 to the 23rd. Okay? I know that that is what 1 mole always equals. So, when I do my conversion, I'm going to put 1 mole equals 6.02 times 10 to the 23rd atoms of zinc. And that's how I place my numbers. Before I get into the calculator portion of it, I am going to cross off my units to make sure they cancel out. I'm left with atoms, which is the unit I want. So now I put it in the calculator, and I get the answer, 1.51 times 10 to the 24th atoms of zinc. For practice, do 11 through 16 showing your work. See you next time.